Welcome to the e-learning course 1, lesson 1, session 1.2. In this session we will focus on time series analysis of past rates of returns. The learning goals for this session are: you know the difference between time series versus scenario analysis. You should be able to compute expected returns, standard deviation, and the arithmetic average, as well as the geometric time-weighted average return. And students should be able to explain the underlying assumption of a normal distribution. Time series versus scenario analysis. In a forward-looking scenario analysis, we determine a set of relevant scenarios and associated investment rates of returns, assign probabilities to each, and conclude by computing the risk premium as a measurement of reward and the standard deviation as a measurement of risk, the proposed investments. In contrast, asset return histories come in the form of time series of realized returns that do not explicitly provide investors original assessments of the probabilities of those returns. We observe only dates and associated holding period returns. We must infer from limited data the probability distribution from which these returns might have been drawn, or at least the expected return and standard deviation. The holding period return. As previously learned, a holding period return of a single period is defined by the expected ending price minus the beginning price plus the expected dividend during that period divided by the beginning price. This holding period return can be for periods with different lengths. To compare different holding period returns with each other, we simply annualize the different holding periods. Let's do an example of calculating the holding period return. Now, if you have an expected ending price of $110 and today a beginning price of $100 and an expected dividend of $4, we can actually compute the holding period return. It's simply the ending price minus the initial price plus the dividend divided by the initial price. Or differently, we can actually say, what is the capital gain? So the increase in price, 110 minus 100 divided by 100, plus the income stream, the dividend, divided by 100. So you see we have capital gains of 10% and a dividend yield of 4%, resulting in a total of 14%. Expected returns. The expected return is simply the sum of the probabilities times the return of each state. Now let's do an example. If you have 3 different states, one is returning 0%, the second 6%, and the third 12%. The probabilities for each state are 1/6, 2/6, and 3/6. As you know, the sum of the probabilities always need to add up to 1 or 100%. So now the expected return is simply 1/6 times 0% plus 2/6 times 6% plus 3/6 times 12% equaling 8% expected return. Expected returns and the arithmetic average. Building up on the previous example, expected returns using the arithmetic average would mean n observations are equally weighted. So n equal 3 for the 3 observations 0%, 6%, and 12%. Now, as you see, every state is equally weighted with 1/3. This would result in an expected arithmetic average return of 1/3 times the sum of 0 plus 6 plus 12%, resulting in 6%. The geometric time-weighted average return. Using the geometric time-weighted average return means that we multiply each period return with each other. Let's assume that over 3 years returns were 0% in year 1, 6% in year 2, and 12% in year 3. This means the terminal value of the investment would have resulted in 1.1872. Annualizing the terminal value would result in the geometric average return of 5.9% per year. After having discussed expected returns, arithmetic average, and geometric average, let's do now a scenario analysis. We can actually do an example where we see the state of the market and the stock index fund in terms of 4 possible scenarios, with probabilities as presented in the table below. How can we evaluate this probability distribution? To start, we will characterize probability distributions of rates of return by their expected or mean return, and in the next step we will calculate the standard deviation. The expected rate of return is a probability weighted average of the rates of return in each scenario. As you see here, we actually get an expected rate of return of 9.76% by multiplying each probability with each return. The standard deviation. The variance of the rate of return is a measure of volatility or risk. It measures the dispersion of possible outcomes around the expected value. Volatility is reflected in deviations of actual returns from the mean return. In order to prevent positive deviations from cancelling out with negative deviations, we calculate the expected value of the squared deviation from the expected returns. The higher the dispersion of outcomes, the higher will be the average value of these squared deviations. Therefore, variance is a natural measure of uncertainty. Variance and standard deviation. Let's calculate the variance and standard deviation of the stock index fund we have previously looked at, where we calculated an expected rate of return of 9.76%. As you have seen from the previous slide, the variance is actually the probability times the deviation of each actual return to the mean. Now, using the numbers above, you actually get to a variance of 0.038. We can also calculate the standard deviation simply by taking the square root of the variance, resulting in 0.1949. The reward to volatility called Sharpe ratio. By now we know how to calculate expected returns, the risk premium, and the standard deviation. Investors are interested in the expected excess return they can earn by replacing risk-free T-bills with a risky portfolio, as well as the risk they would thereby incur. Even if the T-bill rate is not constant, we will still know with certainty what nominal rate we will earn in any period if we purchase a bill and hold it to maturity. The importance of the trade-off between reward, the risk premium, and risk as measured by standard deviation suggests that we measure the attraction of a portfolio by the ratio of its risk premium to the standard deviation of its excess return. This reward to volatility measure was first used extensively by William Sharpe and hence is commonly known as the Sharpe ratio. It is widely used to evaluate the performance of investment managers. The normal distribution. The bell-shaped normal distribution appears naturally in many applications. The graph below shows a normal curve with a mean of 10% and standard deviations of 20%, meaning that 68.26% of all observed returns lie between plus minus one standard deviation, ranging from minus 10% to 30%. The same logic applies for plus minus 2 standard deviations, covering 95.44% of all observed values, and plus minus 3 standard deviations are covering 99.74% of all observed returns. What are the implications of normal distributions? Investment management is far more tractable when rates of returns can be well approximated by the normal distribution. First, the normal distribution is symmetric. The probability of any positive deviation above the mean is equal to that of a negative deviation of the same magnitude. Second, the normal distribution belongs to a special family of distributions characterized as stable. Third, scenario analysis is greatly simplified when only two parameters, mean and standard deviation, need to be estimated to obtain the probabilities of future scenarios. And fourth, when constructing portfolios of securities, we must account for the statistical dependence of returns across securities. So we come to the end of session 1.2. After having carefully studied the slides and relevant chapters in the book, please start with the review questions.